In this video, I intend to demonstrate you a methodology for solving a sample hydraulic problem that uses Bernoulli's equation for a real fluid. The methodology involves the implementation of 4 plus 1 preliminary simple steps. Before moving on to the specific task, let's remind what the 4 steps were and in what sequence they should be performed. The preliminary step, known as step 0, requires for all the parameters from the input data to be converted into basic measuring units only. Step 1, in this case, consists of 2 actions. First is to establish a relationship between velocity and flow rate by applying the equation of continuity. Then is to estimate the energy loss obtained into the pipe system. Step 2 is related to the selection of 2 sections for which the equation of Bernoulli to be further applied. It also consists of 2 actions. Selecting the sections and indicating them on the work scheme, and specifying the 3 typical parameters: absolute pressure, velocity, and geodetic height for the selected sections. Step 3 is just to copy and paste the equation of Bernoulli, in our case for real fluids. And step 4 is to use the data from step 2 and substitute it into the Bernoulli's equation. Finally, the equation to be solved in terms to the unknown parameter. The implementation of the steps is explained in detail in the previous video tutorial, which you can watch at the given link. Information about the video is also provided in the table of contents below. So now it's time to move on to the certain specific task. On the left side of the slide is the work scheme of the task, and on the right is the input data, the information that we have in advance. The studied system is used to transport cold water having density of 1000 kg per cubic meter and being considered as real fluid. Water is transported between the 2 tanks through a connecting pipeline with a length of 25 meters and a diameter of 80 millimeters. The flow rate in the system is known in advance, and it is 12 liters per second. The coefficient of friction, or also known as Mayer energy loss, lambda, is 0.022, and those in local resistances, also called minor energy loss, respectively are: at the entrance, zeta in is 0.5, for an elbow 1 unit, zeta elb is 0.3, at the throttle valve, zeta TV is equal to 4, and at the outlet, zeta out is equal to 1. The pressure in the second tank, the one on the right, is also known, which is vacuumetric, so PV is set to be 150 torrs. The difference between the free water level in the 2 tanks is given by the height h, which is equal to 1 meter. In this task is to be determined what is the manometric pressure PM in the first tank, the one on the left, from where the water is taken. I suggest, as in the previous video tutorials, that now is the best moment to perform the preliminary action, step 0, related to the conversion of all parameters into their basic measuring units, as shown on this slide. For example, in our case, this will be the diameter, which now is 0.08 meters, the flow rate, which has to be presented as 0.012 cubic meters per second, as well as the vacuum pressure, which is equal to 19,995 pascals. It should be taken into account that 1 torr is approximately 133.3 pascals. Before proceeding to the actual part of the solution of the problem, let us discuss the specific features that distinguish real from ideal fluids. The most practical, most simple way to point out the differences is by comparing Bernoulli's equation in its two forms, as shown in this slide. To make it more clear concerning these differences, I will highlight they are colored in orange. The main difference in this case is the indication of the energy loss denoted by HV12, which represents the energy spent to overcome the different hydraulic resistances during the fluid transportation between the two selected sections, conventionally denoted section 1.1 and section 2.2, which will be specified at a later stage when solving the task. This is the so-called step 2. The total energy loss represents a sum of the two types of losses. Those from friction occurring along the entire length of the pipe, depending on the material of the pipe, the time and manner of exploitation, and the flow regime of movement, for which the drum will become in subsequent video tutorials, and those in local resistances. Conditions for the realization of this type of losses exist in every single place where, for one or another reason, the velocity changes its magnitude or direction. These could be narrowings, expansions, elbows, pipe fittings, etc. The coefficients specifying the two types of energy losses involved in the formulas presented on the slide are respectively lambda for friction or Mayer energy loss and zeta for local resistance, also known as minor energy loss. A second specific feature is that in case of real fluids, unlike ideal ones, the flow average velocity must be used. The reason for this statement is illustrated in the following picture. It can be seen that if ideal fluids existed, the velocity distribution in the cross-section would be uniform, which means that at any given point of this section, the velocity would be a constant value. However, this is not the case with real fluids, where the velocity just next to the walls is zero, and closer you get to the center, it starts to increase. In such a case, for the correct presentation of the kinetic energy of the flow, which is one of the members of the Bernoulli equation, the average velocity has to be used. There are various ways and methods of determining average velocity, and some of which will be covered in separate video tutorials. No matter how preciously you determine the flow average velocity, when it is used to calculate the kinetic energy, it is found that there is always some discrepancy, deviation, between its actual value and the expressed by using the average velocity. To clear up this inaccuracy, the Coriolis correction coefficient is introduced, which represents the ratio between the kinetic energy, the actual, and the one calculated with the average velocity. And from the condition that the first is always slightly greater, it follows that this coefficient will always occupy values greater than 1. For turbulent regimes of movement, such as in the task of our interest, this coefficient varies in the range from 1.05 to 1.15. Therefore, the practice is to work with its average value, which means 1.1. Just for information, for laminar flows, it can also reach a value of 2. I hope that now it is clear, and so we can move on to the solution of the certain task. The first step, known parameters, in this case involves performing two actions. The first of which is to establish a relationship between velocity and flow rate. As for this aim, the continuity equation is used. This will allow us to calculate the average velocity of the fluid flow passing through the pipe, since the flow rate is preliminarily known. For this purpose, copy and paste the relevant equation. Then substitute each parameter with its numerical values. And finally, perform the calculation. It seems that the velocity is going to be 2.39 meters per second. The second action to step 1 involves the calculation of the energy losses represented in the form of head. For this purpose, we must consider in advance that the total energy loss represents the sum of the two types of losses which was mentioned before. It is logical to calculate them by suggesting that we start with friction MER, also called energy loss, like shown on the slide. Initially, the formula that can be seen on this slide is used. Then it is replaced with numbers, and after being calculated, for the friction energy loss, it is obtained 2 meters. It is now time to calculate the local resistance, also called minor energy loss. And this can be done according to the equation presented in the slide. Once again, the parameters must be substituted with their numerical values, as I only find it necessary to discuss the calculation of the summarized coefficient of local resistances. For convenience, I suggest adding up all the individual local resistances coefficients, like shown, just look the ones colored in orange, remembering that their values are valid and applied for 1 unit. What does it mean? In our case, there are two elbows, it can be seen on the work diagram, which requires that the coefficient zeta k to be multiplied by 2, which means by the number of local resistances of the same type. All that remains is to perform the calculation, on the basis of which it is found that the local resistance, also called minor energy loss, is 1.78 meters. In order to complete step 1, it's necessary to go back a few rows higher and sum the values obtained for the two types of energy loss, thereby enabling the final calculation of the total energy loss in the pipe system. In this case, the total energy loss will be 3.78 meters. Now we can easily move on to the implementation of step 2. This step, I am just reminding you, consists in correctly selecting two sections for which it will be subsequently applied the Bernoulli equation. in the case of real fluid, of course. In order to avoid any possibility of making a mistake regarding the selection of the sections, I would like to remind you the unwritten rule that has already been discussed in the previous videos. It's only necessary to follow both ends of the height h, which takes you to the places where you need to select the sections. So after applying this rule, in our case, this will be section 1.1, the level of water in the left tank, and section 2.2, the level of water in the right tank. Be sure to indicate the places on the diagram where the two sections are selected, as demonstrated in the sample work diagram presented on the slide. The next action is related to the description of the work parameters in the previously selected sections, which I propose to perform combined for both. The determination of the absolute pressure for the two sections is performed as follows. For section 1.1, since the tank is closed and manometric pressure is acting, the absolute pressure will be represented as the sum of the atmospheric and the corresponding manometric pressure. For section 2.2, the case is analogous, but it should be taken into account that vacuum pressure is acting there, which means that the absolute pressure in this case will be represented as the difference between the atmospheric pressure and the corresponding vacuum pressure. The velocity in both sections will be zero. It is known, I'm just reminding, and should be remembered as a rule to always apply in such cases, that the velocity in the uppermost liquid layer, the so-called free level of the liquid in the tank, is reliably small, insignificant, which means that it is assumed that V1 will be equal to V2 equal to almost 0 meters per second. To determine the values of Z for the two sections, I remind you the rule that we derived in one of the previous video lessons. For the section that is closer to the Earth's surface, Z is equal to 0. We accept this. And for the section that is further away from it, Z is equal to h. In this specific case, applying that rule, it seems that closer to the ground section is 2.2, which means that Z1 will be equal to h equal to 1 meter according to the input data, and Z2 will be equal to 0. Performing step 3 involves only rewriting copy-paste Bernoulli's equation for a real fluid, as shown on the slide. It's time to move on to step 4, which is the last one. And this means that we have to use the data from step 2 and substitute with it in the Bernoulli equation. I will continue to advise you to always make the initial substitution symbolical instead of numerical, as shown on the slide. The parameters colored in orange are about to be truncated, eliminated, leading to a simplification of the equation. So after removing the unnecessary terms of the equation, the following expression, final equation, will be obtained. Its solution must be performed in terms of the unknown parameter. In this case, this is the manometric pressure PM. So next is the numerical substitution, and after which the pressure is calculated. Ultimately, the manometric pressure will be 7,000 276.8 pascals.